Better? Yeah, okay, sorry. Yeah, so I'm going to move a little bit towards open systems in a couple of different ways. So the first thing I'm going to do is I want to go through very important results in I would say thermodynamics of quantum systems. The first work where this type of stuff was sort of hammered out was in the paper by Massimiliano Esposito and some collaborators, Lindenberg, van den Broek, in around 2010 in an NJP. And the same result, more or less, was sort of rediscovered by Michael Wolf and David Reeb around 4 years later in another paper in NJP. So that's Reeb, Wolf, NJP 16103 011 2014. And in the first paper, I think if I remember correctly, it's called entropy production as a correlation between a system and reservoir, something along these lines. So it's more focused again on this irreversible entropy production in a framework that I'm just going to discuss in a second. And the paper by Reeb and Wolf, which contains exactly the same mathematical result, sort of puts more emphasis on this being connected to Landau erasure, so the logical irreversible sort of manipulation that gives you entropy production in sort of thermodynamics, or in computation, I should say. But they do a lot more than just I'm going to talk to you about. I mean, they provide all sorts of lower bounds, finite size corrections, all that kind of thing. It takes much longer, but I'll give you the bare bones so that you can read these papers and you know, you'll understand more or less where you're going. So the other thing I wanted to say is that a few people asked me about the notes from this. Actually, the plan is this. So as I said, you know, I have based a lot of a course that I taught in Trieste, you know, 8 years ago or something like this on some of these topics, but also with a former postdoc of mine who now works in Auros, Archak Purkayashta. We've actually been putting together a sort of tutorial that we're going to put on the archive and submit it as a tutorial to maybe PRX Quantum or something like that, but because timescale is diverging in terms of being able to do that, it's a long-term project, I'm not sure, but it will be basically based on many of the things that I'm talking about today. So this is going to be the first taste of open systems. I could do a lot more, but I don't have time, so I like this result, or this particular derivation, because it encapsulates, again, the importance of relative entropy in thermodynamics. So, you know, what we're going to be, the situation that we're going to be considering now is some system with Hilbert space Hs, an environment He, okay, and actually there's going to be no condition on the initial state of the system in this case. There'll only be a condition on the initial state of the environment, right? So the environment state, let me call it rho E, will be prepared in a thermal equilibrium. This is the Hamiltonian of the environment, okay? And I'm going to assume that initially, okay, the composite state of the system environment is going to be prepared in a product state, with the system state being arbitrary, okay? Again, apologize if I abuse notation. Hopefully it'll be clear, okay? So that's the situation, starting off in a product state, arbitrary state for the system, thermal state for the environment. And then we're going to basically couple the system and the environment through a unitary, okay? So the environment is going to have a finite dimensional Hilbert space as well, right? I'm not taking any sort of n go to infinity limit for the environment. You can think of it as a fairly large system. You could interchange the role of either, right? It doesn't really matter, but one of them is starting off in a thermal state. We call it the environment. And the system environment state, it evolves in time under this unitary. So this Unitary, of course, can describe, if you like, it can describe a switch on of system bath Hamiltonian, a system environment Hamiltonian, okay, at time 0. Then you get evolution of the entire composite state into some state that we call rho prime SE. Yeah? Right, so let me just define some things first that we're going to need. So let's define entropy, von Neumann entropy decrease of system as delta S, which is S of rho S minus S of rho S prime, okay, where rho S prime is the trace over the environment of rho SE prime, okay? The entropy change in the environment is, we just say delta. This is going to be rho E minus S rho E, where rho E prime is the trace over the system of rho SE prime. So now what we want to describe is the heat exchanged between the system and the environment, okay? So how do we define that? Well, it's going to be the energy change of the reservoir, okay? So the heat transfer to the environment we define as, let me call it Q, is the trace of HE rho E prime minus the initial energy of the environment. So in this framework, the state of the environment changes under time evolution, okay? This is just the energy change up to some time in the environment, and we define that as the heat. The Hamiltonian of the environment doesn't change, okay? It's fixed. So if you want, in your mind, think about the situation where I start off with some Hamiltonian, which could be HS plus HE, and then at time 0, I turn on a coupling, H interaction between the system and the environment. I wait some time, and I turn off the environment, and I measure the energy change in the environment, and that would be the heat, okay? The other object that we'll need, and I guess you've all heard about it, is the mutual information. So the mutual information between A and B, generally speaking, is given by the von Neumann entropy of A plus S of rho B minus S of rho AB, okay? So this, what does this quantify? The mutual information measures the correlations between A and B, both classical and quantum, okay? It doesn't differentiate between entanglement or anything, just the total correlations in this bipartite system. And that actually, the mutual information in general can also be written as a relative entropy, okay? This, I guess people know, that you can always say that this is the relative entropy, the quantum relative entropy between AB, okay, rho A tensor rho B. They're equivalent. Okay? So obviously if you have an uncorrelated state, the mutual information is 0, and this is a measure of the correlations between state A and state B. And we're going to use this now at the level of the system and the environment. Okay? So let me first sort of prove a lemma. And the lemma is that the entropy change of the environment, delta, yeah, is equal to the von Neumann entropy change of the system, delta S, okay, plus the mutual information between the system and the environment. That's what I want to prove. So it's pretty straightforward. So let's look at delta minus delta S. Okay? This is just S of rho S prime minus S of rho S plus S of rho E prime minus S of rho E. These are all operators, and I'll be sloppy from time to time and forget the hats, but you know what I mean. I hope it'll be clear. Right, so this is equal to S of rho S prime plus S of rho, just rewriting it, okay, minus S of rho S tensor rho E, right? Because of the additivity of the von Neumann entropy for product states, okay? Now, notice that this guy here, yeah, is the same as the entropy of rho SE prime, because it's unitarily connected to rho SE prime and the entropy doesn't change under a unitary, right? So this is equal to S of rho S prime plus S of rho E prime, yeah, minus S of rho S E prime. Because these things are unitarily connected. Clear? And there you have it, right? By definition, this thing is the mutual information of rho SE. Yeah? So this is I S dash E prime by construction. And because that's a relative entropy, due to Klein, this thing is greater than or equal to 0. Because it's a relative entropy. Okay? All right, now let's use that, and so what have we shown? So let's use that. Are people okay? Can I move page? Yeah. Okay. So let's use that. So delta S plus I S prime E prime is equal to S rho E prime minus S of rho E. Okay? So let's work with the right-hand side. Okay? This is equal to minus the trace of rho E prime log rho E prime plus the trace of rho E log E to the minus beta, and this is why I'm doing this will become clear in a second, ZE. I've just written down explicitly the form of the von Neumann entropy for rho E prime and rho E. So this is equal to plus the trace of rho E, okay, minus beta HE minus identity log, okay, trace of E to the minus beta HE, okay, just a rewriting. Okay, now this is equal to just breaking up the trace, okay? Trace of HE rho E minus the log of the trace of E to the minus beta HE, okay? And now I'm going to add and subtract the following terms, minus beta, sorry. So add and subtract the following terms, trace HE rho E prime minus beta trace of HE rho E prime. Right? Okay, and now you see that this thing, okay, is trace of HE, rho E prime minus rho E, plus, I'm going to write this thing out, trace of rho E prime log E to the minus beta HE all over the trace of E to the minus beta HE. Okay? Just a rewriting. This one, yeah, is beta Q. From the previous definition, okay? And you see that this part here, yeah, is minus, and you get this guy, which is S rho E prime, yeah, rho E. The relative entropy, yeah. Yes. Sorry? Like the trace of the identity is like D. Yeah, sure. I mean, yeah. Let me think. Yes, there's somehow this thing is coming in. I'll come back to you, okay, on that. I off the top of my head, I can't remember why this, but I'm sure it's nothing. Is it even necessary? I don't even think it's necessary to put there. I mean, so it's okay. I'll come back to you. Let me think a little bit about it. Okay, so what have we shown here? Well, you've shown that beta Q, okay, minus delta S is equal to the mutual information, okay, between the system and the environment at the final time, right? So after you do your switch on and switch off of the unitary, plus the relative entropy between the environment state at time tau and the initial time. Okay? So let's look a quick look at this thing. This is important. So as you remember from second law, yeah, this thing is the entropy production, right? Beta Q, the reversible heat exchange, minus the von Neumann entropy change, now with a different sign convention than what I used in the first part of the lecture, but doesn't matter, okay? Is equal to the mutual information, which is a relative entropy between rho SE prime and rho SE, so it's positive, and another relative entropy term which describes the perturbation of the environment by its interaction by the system, which is also positive, right? So because it's a sum of two relative entropies, beta Q minus delta S is positive. The entropy production in this scenario is positive, and this object here plays the role of the irreversible entropy produced in this scenario, okay? Now it's interesting, this relation. Think about what it means, or what does it tell us? It tells us that there's two contributions to the irreversibility on average here. The first one is a contribution from the correlations that are built up through the coupling between the system and the environment, okay? And the second one tells us that how the bath is influenced by its coupling to the system also gives you another contribution, right? So obviously, in the situation of ultra-weak coupling, and when you have a massive bath in comparison to the system, you can see that somehow you're recovering a kind of reversible ansatz where this thing will be 0, right? So this was what Massimiliano Esposito and others first found in 2010 or so, and they comment on this, about these two individual terms. And then Rieb and Wolf sort of interpreted this in the context of Landau erasure. For example, we didn't really specify that the system state at initial time was necessarily thermal, right? It could be anything. So for example, you could imagine doing some, like rho s is the information bearing degree of freedom of some computer, okay? And you do some erasure protocol, or some logically reversible protocol, and you can see that you can kind of analyze, you know, sort of gates at the level of the system in the environment in this context and compute the dissipation induced by the gate, and they interpret this in the context of the Landau erasure problem. But it's just the entropy production in the sort of standard language of thermodynamics. So it's a very useful relation that you can build on, actually, many things. So as an exercise, okay, you can try to put this in the following form, which is equivalent, which is in the Esposito paper, okay? This is equivalent to the relative entropy between rho SE prime and rho prime S tensor rho E, okay? Where again, rho SE prime is U rho S tensor rho E, and rho S is the trace E of rho S E prime. So you can show that this form is equivalent. That's as an exercise, okay? A few lines. They're the same. And also positive by Klein, okay? Of course, because it's the same. I want to make a comment, which is very interesting to me, and it's, you know, it's something that, I mean, it wasn't entirely obvious until I saw it. There is a nice paper, relatively recent, I would say 2000, correct me if someone here knows it, could be 2020, 2019, some year of the plague. The following paper came by Esposito and a name which I find very difficult to pronounce. It's a PRL 123 200603. Okay. 2019, I can give you the reference in general, okay? They used a result which is a corollary of the Araki-Lieb theorem, okay, which I don't want to get into, but anyway, what did they show in this paper? They showed that the mutual information term, okay, this term here, is bounded from above, okay? They show that it's bounded by twice the log of the dimension of Hs. That's very interesting to me. It shows you that if you have a small system, so this is the result, right? If you have a small system, yeah, dimension of the Hilbert space of the system is much smaller than the dimension of the Hilbert space of the environment, then the mutual information contribution to the irreversible entropy change is bounded above by something which is log of volume of system, right? Which means it can't be very large. So at long times, you know, even in this system environment sort of setting, the entropy production is dominated by the relative entropy of the bath states. And this makes a lot of sense because one of the topics that I'm very interested in, which I don't have time really to get into today, is non-equilibrium steady states. Okay? In a non-equilibrium steady state, you have multiple baths. You have two baths. And you take the long time limit, okay, and you get currents, the STT is 0, etc. But we know in a non-equilibrium steady state that the entropy production scales like T. So you have to use the time integrated quantity and divide by T. So the entropy production in a non-equilibrium steady state is unbounded, okay? So it must be dominated by the relative entropy between the environmental states. And this came as a surprise to Massimiliano and others because they always thought that somehow it was subdominant contribution, but in fact it's the dominant contribution. So the mutual information term is actually subdominant. Irreversible entropy.
So there are these two contributions, right? One which is due to the correlations, and the other which is sort of, let's say, more thermodynamic. You're looking at how the bath changes, and in this way, you're kind of able to say, okay, the bath changed, so there's some heat exchange, and we can keep track of that. One thing which has always kind of confused me a bit here is that it's somehow clear to me that the correlations, that is irreversible, right? You've built up correlations, this is irreversible. But when somehow the thermodynamic process, like this heat exchange with a bath, when is that irreversible, and how should one think about that being irreversible, you know, in this context? This notion of when is something truly irreversible, this is what I'd like you to comment on.
So that is something truly, okay, so this is, of course, an average. The work thought, there's another way of thinking about this from the perspective of work. I mean, I didn't discuss the work in this context, but you could think about the work as well and play the same game as I did in
the first lecture, so where you try to define the work minus the free energy difference, but now the work is defined not on the system, but on the system environment, right? So the whole thing. And you can show that actually, if you prepare
the system in thermal equilibrium state as well, yeah, that if you compute the average work minus delta F, or the average work minus the energy change of the entire system environment, is fully consistent with the above result, right? So, and fully consistent with the first part of the direction. As for your statement about, you know, somehow,
what does it mean for it to be truly irreversible? I don't know. I mean, this is just how the entropy production is defined. I should make a comment as well that it's the entropy production itself which is strictly positive in non-equilibrium thermodynamics. The rate, the time derivative of the entropy production is not positive in general, okay? It is positive only in two situations that I know, okay? It's strictly positive, I mean. It is strictly positive for semi-group dynamics. So if you have a Lindblad master equation describing the evolution of your system, you can use this famous result by Spahn, which I was going to include in this, but okay, I don't have time, which shows that the rate is positive for Lindblad with thermal fixed points. Or in a generic situation, if you take the long time limit, the entropy production rate of a non-equilibrium steady state can be shown to be positive as well, okay? So positivity of the entropy production is, I mean, that is a theorem above here. I mean, on average, this is a theorem. If with minimal assumptions, the only assumption really is that the environment is initially thermal. System is arbitrary, and you couple via unitary, and this is, you know, a fairly straightforward, when you see it, of course, right? So it's a different thing coming up with that, but yeah. I probably didn't answer your question, but I don't know what it really means to be truly irreversible. Like. Yeah, I mean, look, I mean, there's also, I should mention that I'm assuming thermal equilibrium states are described in the framework of canonical thermodynamics. There is a way, this is something that I've actually worked a bit with Mark on, we've discussed many times, there's actually a way of thinking about this in the micro-canonical framework, okay, which is in some sense more fundamental than the canonical framework, in my opinion. But it's beyond the scope of what I'll talk about today. But I wanted to mention this paper by Esposito, and I won't even, maybe Christia, you can pronounce the name properly. It's like, I wouldn't do it justice, but this Polish author, it's interesting, and something that you can really see that if you have a situation where the system is much smaller than the environment, then in the long, well, I mean, it's bounded, basically, that contribution, whereas the relative entropy is unbounded from above. I mean, it can grow arbitrarily large, and in fact, it scales like t in non-equilibrium steady state, scales like time, okay? Okay, so actually, I want to go on to a multiple bath scenario next, okay? So this is sort of single bath system. The only assumptions are thermal state for the environment, arbitrary state for the system. But you can also sort of see that there's a lot of interesting things happen when you put multiple baths, okay? So, so this is, okay, there's a bunch of different works on it. There's a nice paper by Campisi, Fazio. It's a JPhys A around 2016. And they consider, you know, the scenario where you have more than one. You can have multiple ones, right? So you have some bath described by temperature 1, chemical potential. You can even include other conserved quantities. Okay, we haven't talked about the grand canonical ensemble, but I'm going to drop it anyway in a second just because it's not really necessary for what I'm going to talk about next. So you can have multiple temperatures, okay, in some system. And the system now, it exchanges particles and energy with all baths, okay? So, L of them. So if you want the total density matrix initially, okay, is going to be rho S times 0 tensor product of these grand canonical states for the baths. So H BL minus mu L N BL all over Z BL, okay? Generically speaking. Let's include a Hamiltonian now. So the total Hamiltonian, which is some parameter S, we give a Hamiltonian for the system plus some system BAT coupling, which we can allow be time dependent, plus some BAT Hamiltonian. Environmental Hamiltonian, again, I've abused the notation, but don't worry, so it's okay. Okay. So HSB, okay, we're gonna write it as sum over L HSB S GLS, where GLS is some function of time, which allows you to describe how you switch on and switch off the system back coupling, okay? And HB is going to be sum over L HBL, okay? So we can assume for now, without any loss of generality, I'll come back to it, the situation when we set the chemical potentials of the baths to be 0, okay? So you're back to the situation of canonical states for the baths, but I'll return to that in a second, okay? So what is the work done? And now imagine you switch on, okay, you switch on, for example, the system bath coupling interaction. You could also include a time dependence at the level of the system. Have in mind whatever you want. The work done, let's call it external work now. Okay, I'm just being a bit pedantic because I'm going to introduce a chemical potential at some point, which is going to give me some chemical work. Okay, up to time tau, yeah, is the expectation value of h of tau. Okay, where I mean in the Heisenberg picture, and the average is taken with respect to the initial state. Okay. And again, you can define an isothermal deviation. So I'm going to assume now that the system, yeah, was also prepared in thermal equilibrium, which I didn't assume in the last example. So at time 0, the system is also going to be at some temperature beta S. Okay? And all these temperatures can be different in general. So the isothermal deviation, which is this average work, which again, is the energy change of the entire complex induced by the unitary, which couples the system and the baths together, right? Is the average work minus the sum over L delta F L. Now, let me abuse a little bit the notation and say that L in this particular case is going to represent system, BAT1, BAT2, up to BL, okay? Just in this particular case. So, delta F, yeah? Delta FLs, think about it. The bath Hamiltonian, right, is time independent, yeah? So delta F for the baths, all the baths is 0. The only delta F contribution is at the level of the system because the Hamiltonian of the bath is time independent, and this is delta F's of a reference isothermal process, like we discussed in the first part of the lecture, right? So you can write down this entire thing, okay, sum over L, beta L, where now this sum also includes the sum over the system times the dissipation at each plus the system contribution. So, okay, L not equal to S. Again, I'm abusing a little bit, but you get what I mean, right? So HS T minus HS 0, okay, plus this free energy change ZS tau over ZS 0, okay? So again, using that result by Donald, right, you can show, so the relative entropy between rho s at time tau, okay, the initial thermal equilibrium state of the system is equal to minus s rho s tau, the von Neumann entropy at time tau of the system. So that's system trace out the environment, okay? Plus beta s hs tau plus log of zs tau. So this comes from this result of Donald, right? This is something that you can show. So now, let's just put that in here, okay? What does it become? It becomes sum over L, beta L, W this is equal to sum over L, beta L, HBL tau minus HBL 0 plus this term, relative entropy rho s tau. You kind of have to stare at it, but minus s of rho s beta 0 plus s of rho s tau. Okay? Similarly, you can write the relative entropy between the bath states at time tau and their initial states. Just put a beta there to say that it's the same thing, minus s rho beta L tau plus beta L HBL tau plus the log of z beta L tau. So this, putting it all together, you find that beta L HBL tau minus beta L HBL is equal to the relative entropy of beta L tau plus S of rho beta L of tau minus the S of rho BL0. Now we're going to write down an expression for the dissipative work. Sum over L beta L W this using above is sum over L S rho beta L tau relative entropy with rho beta L 0. This is thermal equilibrium states, plus the relative entropy rho S tau rho S beta 0. So it's a bit laborious. Plus sum over L S rho beta L tau plus S rho S tau minus S of rho total at time 0. Okay? So you can manipulate the expression down to this form. Sorry if there's a bit of sloppiness there. It's a bit of a tedious thing. And actually, so S of rho total at 0, okay, is equal to S of U rho total 0, U dagger, which is, of course, equal to S of rho tau. Yeah? Now the total correlations, I'll explain, of rho total tau, the total amount of correlations between the system and all the bats together, okay, is defined as the sum over L S rho beta L tau, okay, plus the entropy of the system at time tau, okay, minus S of rho total at time tau. This is actually a relative entropy, okay, between basically all components and the total state. Okay, by definition, because it's a sum. This is the sum of all of the marginal entropies at time tau minus the entropy of the total correlated state at time tau. So this describes the total correlations between all bats in the system. Okay? So the conclusion of all of this, okay, is that the entropy production, which is the sum, and this is in the Cambisi-Fazio paper, beta L W dis, okay, where now I've switched back to the abusive notation of S B1, B2 up to BL, okay. This is equal to the sum of L not equal to S of the lags, or the relative entropies of the components, okay, and their initial states, plus S of the system, plus the total correlations at time tau. These are all relative entropies, okay? But you have a very nice generalization of the Esposito result to multiple bats that kind of makes sense intuitively. This term, okay, here is just how each of the bats change in time by their interactions with everything else. This is how the system changes. And there's this contribution, the total correlations between this system and all the bats together, right? You can prove that this is formally equivalent to the entropy production, which is the sum of the dissipative work in the entire composite thing, okay? Okay, so where am I? Okay, good. So I think what are we doing? We've got 5-10 minutes before a break. Is it good? I think it's 5-10 minutes before the break. Okay, so this is the generalization. This is in the Capizzi-Fazio Journal of Physics A, right? So seeing this sort of total correlations in terms of the dissipative work. Now it's useful, okay? So you can also show that this is equivalent to basically, well, okay, maybe what I was going to say is that let's so this epsilon at time tau, or say sigma at time tau, big sigma at time tau, okay, I would use the following. This was something that you should have proved, or you will prove, that this is equivalent to this Esposito-like result, okay, tau, rho s, tau, product over L. So I didn't prove this. This was an exercise in the one bat case, but it's okay, you can get the gist. So why am I taking the limit of the bat dimension to go to infinity, right? There's a reason for that, well, maybe I won't get into, but somehow, you know, if you want to be very, very sort of pedantic, to really define the bath as a bath, maybe it's wise to take the limit when the bat dimension gets large. But you can show that this thing, okay, is equivalent to sum over L, beta L, Q L of tau, okay, minus delta S, okay, where this thing is S rho 0 system, okay, minus S of rho tau. So I leave this because time is pushing on. I leave this equivalence because it's pretty laborious to show that, you know, you can define the entropy production as the sum of beta L times the dissipative work, but if you manipulate, right, you can also show that that's equivalent to just summing up the heat exchange in each bat minus the von Neumann entropy change of the system, okay? What happens if you get a chemical potential, right? So I didn't derive anything with respect to a chemical potential in the bath. So what would you think happens when you get a chemical potential? I mean, what happens essentially is you get another contribution in chemical work, okay? So you're going to get another contribution in chemical work. It's not too difficult to see. It's exactly the same. It just becomes even more laborious. But you get another term which is equal to minus sort of mu L N L tau minus N beta L, okay, beta L 0, okay? The derivative, yeah, of the time derivative of this object, this chemical work, okay, is going to be essentially the particle current, whereas the time derivative of the heat exchange is going to be the heat current, okay? Sorry, I apologize. There's a bit of confusion here, and then I'm after confusing myself, now I'm after realizing. There is a subtlety. When you have no chemical potential, the derivative of the energy change of the bath, yeah, is the energy current. When you have a chemical potential, yeah, the definition of the heat current is the energy current minus mu times the particle current, okay? This is a subtlety. It's not very important, including like a chemical potential is nice, right? Especially if you want to deal with fermionic bats, like in mesoscopics, it becomes very important. But you know, the question is now, before we finish up for the last sort of part of the lecture, the question is all of this meaningless because it requires you to measure the density matrix of the bath and how it evolves in time, okay, to do thermodynamics. But actually, you're saved in some sense, because what you can always do in the multiple bath scenario is you can measure the currents flowing through the system and time integrate the currents to get those objects. Okay? So let me show you. So imagine I want to measure in the lab HBL of tau you know, minus HBl tau. This is minus the integral from 0 to t ds of j bl going to s of s, where j bl going to s, for example, is minus the derivative of HBl dt. You see, as an experimentalist, you wouldn't measure the actual change of the bath's energy. You would measure a current coming from the bath to the system and time integrate that. It's equivalent. You see? So you can do the same for the particle currents. So usually in an experiment, you know, when you talk about energy currents, particle currents, and all that type of stuff, when you're doing thermodynamics and you want to connect to the entropy production, you typically do time integrals of the currents, right? It's easier to measure. It's another point that I wanted to make, okay? And now the next step, which I'm not going to, okay, because I'm moving on to something else after the break, is if you were to take this to the next step, which requires another bit of time, the next step is to take the t go to infinity limit, okay? To take the t go to infinity limit with multiple baths, you're in the situation of non-equilibrium steady states, right? So this is the situation where you generate, you know, currents, okay, but d rho dt is 0, yeah, of the system. There is still a lot of open questions in the thermodynamics of non-equilibrium steady states, okay, which are still unanswered. It's sort of, in my opinion, a topic which, you know, although there's lots of work, in particular in mesoscopics, experimentally, from the theoretical perspective, linking to information theoretical quantities like the relative entropy in the non-equilibrium steady state, so the long time limit of a multiple bath process, is still an open question in many ways. The reason that's problematic there, why it's problematic, is because the correlations between the baths, okay, in the t go to infinity limit, yeah, they're not negligible, okay? So usually, if you come from an open systems background, your natural inclination would be, let me write down a master equation and assume additivity of, you know, the dissipators in each bath. So Mark down there has a very nice paper a few years ago with Martin Plenio describing that. Look, in general, you know, the global sort of thermodynamically consistent master equation, the dissipators, you know, essentially are not additive because, precisely because, if you see it in my way anyway at least, it's you have a term which basically is here. You can't get rid of that, yeah? So the assumption from the offset that your dissipation is additive is flawed, okay? If you want to derive effective master equations for the system. You have correlations between the baths, which are mediated by the system, okay? That's a problem, and it's a technical issue, and many people are working on methodology to sort of get around that. But for thermodynamic consistency, it is a problem in the long time limit because those correlations dominate. So we leave it at that, and we'll do the last bit after a break.